All right, so this is where we left off in class. So what we were talking about was that if you wanted to find the directional derivative of a function, that's just equal to the dot product of the gradient of f dotted with u. Okay, so this is what we were covering in class. So you can find the derivative at any point in any direction, and that will depend on wherever u is. So remember, grad f, the gradient is just the partial derivatives with respect to x and with respect to y. And u here is going to be a unit vector. So this is the direction. So you want to know what it will be the derivative in the direction of u. So that's what we call the directional derivative. So what's happening here is that we're just extending this to three variables. So instead of having our two components, now we have our three components, f sub x, f sub y, and f sub c. So here we're just extending it to more dimensions. So remember here again, u is going to be a unit vector. So if we have a vector v, we need to make sure that we make it into a unit vector. Okay, so let's go ahead and take look at this problem. So we have f of x comma y comma z is equal to x sine yz. We want to find the directional derivative of f at this point in this direction. So let's start off by knowing that we're going to use this formula. And let's take the gradient. So grad f. So we're going to take a partial derivative with respect to x. So the x goes away and we just are left with sine of yz. The partial derivative with respect to y. So that means you're going to get the x by itself. Derivative of y would just be 1 times z. So that's going to come outside. And you have the cosine of yz. And then the partial derivative with respect to z. So that will bring out the y. So you'll have xy cosine of yz. And what I'll do is that I'll go ahead and plug in the point already. So I'm going to put in grad f, and I'm going to plug in the point 1, 3, 0. So that should give me the sine of y times z, which will give me 0. Then you're going to get 0 cosine of 0. And then 3 cosine of 0. So you can see that the first two components will just give me 0. And then the last one will just give me 3. So this will be the gradient, okay, at that point. And now what we're looking at is, well, we got the gradient, so now we got to find the unit vector, so u. So you can look at v and see, well, v is not quite a unit vector, so we're going to have to normalize this by dividing by the magnitude. So you're going to have 1, 2, -1 divided by the magnitude, which is going to be 1 squared plus 2 squared plus -1 squared. All right. So on the bottom, you're just going to get 4 plus 1 plus 1, that's square root of 6. So you're going to get 1 over square root of 6, 2 over square root of 6, and -1 over square root of 6. All right, so this will be my unit vector. And now all we really have to do is just now take the dot product. So you're going to get the directional derivative is going to be the dot product of these two guys. So grad f dotted with the unit vector. So this is going to be 0, 0, 3 dotted with 1 over square root of 6. 2 over square root of 6, and -1 over square root of 6. So you can see the first two components will go away. So you just have 3 and the -1 over square root of 6, which will give me -3 over square root of 6. So this guy will be the directional derivative at this point in this direction. So what do we want to do now? So we know that whenever we have a function, all right, so let's say we have a function, and let's say you have some surface, and we're trying to figure out at some point, we want to know in which direction is a derivative going to change the fastest. So you know that we can go into many different directions. We can take the derivative in many directions, but which one is going to be the one that's actually the fastest, in which direction? So that's kind of what we want to do. We want to maximize the directional derivative. So let's say we have a function f, and we are considering all possible directional derivatives of f at a given point. So we want to know what direction is f going to change the fastest. So which unit vector should we use? Or what vector? So here's the theorem. So suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the magnitude of the gradient. And it occurs when u has the same direction as the gradient vector. Okay? So here's a little proof, mini proof. So we know that the directional derivative is equal to the gradient of f dotted with the unit vector. Okay? So remember from before that if I have the dot product of 2 vectors, that's just equal to the magnitude of u, the magnitude of v, times the cosine of theta. So that's kind of what's happening here. I'm using the same formula. I'm taking the magnitude of f and the magnitude of u times the cosine of theta. So we know that the magnitude of u is just going to equal 1 because that's just a new unit vector. So we have the magnitude of f times the cosine of theta. Now, when is this maximized? Well, this guy's going to be maximized. Well, if we think about what cosine is, cosine has a range of -1 to 1. So cosine will be maximized when it's equal to 1. So when this guy is equal to 1, so you're going to have the magnitude of grad f times 1. So basically, this will be maximized at the magnitude of f. This is what this looks like. Okay, so hopefully this helps to figure out why this is true. I know that it's kind of a little bit, not as, you can't really see it and be like, oh, that's what it is, but this is just how you would do it to kind of prove it. All right, so that's going to be the fastest. So let's go ahead and do this example. So suppose f of x comma y is x e to the y. So let's find the rate of change of f at the point p, point 2 comma 0 in the direction from p to q. All right. So here this problem is given to you a little differently. And notice that this is just a fancy way to just say find the directional derivative. Because remember, rate of change means derivative. Okay, so this is derivative. That's just a fancy way to say derivative. And we want in a direction from p to q. They're giving you a direction. So in other words, what you're finding for is a directional derivative. Okay, so we're looking for d of u of f, which is going to be equal to the gradient of f dotted with the unit vector. Okay, so let's start off piece by piece. So the first thing that we want to do is take the gradient. So let's go ahead and find that out. Oops. So the gradient in this case is going to be partial x and partial y. So we look here, the partial x is just going to be e to the y. Partial y is just going to be x e to the y. All right, so let's go ahead and plug in the point grad f of 2 comma 0. So I'm going to plug in 0 for the y, that's just going to give me a 1. And then I'm going to plug in the 2 here, e to the 0, that's just going to give me a 2. All right, so just plugging in this number. I'm just plugging in these numbers in here. Okay, so that gives me the gradient. All right. Now what we got to do is find the vector. Okay, so the vector v is going to be basically whatever the vector is from p to q, the vector pq. So remember, that's the terminal minus the initial. So in other words, it's going to be the 1/2 comma 2 minus the 2 comma 0. Okay, and this is going to give me, so 1/2 minus 2 gives me -3 halves. And then the other one's just going to give me a 2. Okay, now remember, this is not a unit vector. Okay, so this guy is not a unit vector. So we need to make it into a unit vector by normalizing it. So you're going to take 3 halves and then 2 and then divide it by the square root of -3 halves squared plus 2 squared. Okay, and what that will give me is -3/5 comma 4/5. Okay, so here is my gradient vector and this is my unit vector. All right. All right, so what I'm going to do now is I'm just going to take the dot product. So this is going to give me 1 comma 2 And I'm going to dot it with negative 3/5, 4/5. I'm going to take the dot product of this guy, so you're going to get negative 3/5 plus 8/5. And this is just going to give me 1. All right, so this is going to be the directional derivative. Okay. All right. So now what we're looking at in part B is, in what direction does f have the maximum rate of change? And what is the maximum rate of change? Okay, so remember, the maximum rate of change will be the fastest at wherever grad f is. So the maximum rate of change will occur at grad f, okay? And in particular, it's going to be so this will be the direction in which it will change. So this will be the direction, okay? And the actual rate of change will be whatever grad f is, okay? So the direction, so because we're looking at the point 2, 0, right? So we're looking at the point 2, 0. The direction of this guy, so the direction, which in this case will be grad f at 2, 0. And we found that vector in the previous one. It was this guy, 1, 2. So in this direction is where the change will be the maximum, okay? So then what is the maximum rate of change? So what about if we were looking for the maximum rate of change? Well, that's just going to be, so max rate of change is going to be whatever the magnitude of that guy is. And we know how to do that. That's just going to be the square root of 1 squared plus 2 squared, which equals square root of 5. So this will be the maximum rate of change, okay? Now, what exactly does this mean? Okay, so if you were to kind of graph this guy, and what I'm going to do is I'm going to look at the level curves of this function, x e to the y. All right, so if you look at the function f of x, y equals x e to the y, all right? So let's go ahead and graph it. So I'm going to look at the contour map of this. So if you kind of look at a contour map of this, and you can use the website that I gave out in class. So here's 1/2. Let's say this is 1/2. And let's say this is 2, because that was where Q was at. And then here is 2, 0. This is where P was at. And if you kind of look at the level curves, they kind of look like this. So they kind of look like this. All right. So that's kind of what this looks like. So what this is really saying, what the maximum rate of change is saying is that, okay, so starting at the point 2, 0, because that's kind of where we started off. For part A, what we did, we calculated the slope, right, in this direction at PQ. Okay, this was the slope, and what we got was that the slope from here to here in this direction was equal to 1. That's what part A was talking about. This was equal to 1. Now, what the maximum rate of change is saying is that, no, the actual direction in which this is going to change the most, because you can go into any direction that you want, but the one that's going to give us the steepest slope is going to be in the direction of the gradient. So notice, in the direction of the gradient, that's 1, 2, that's going this way. So you're going over 1 unit up 2, that's going in this direction. And the slope in this direction is going to be the square root of 5. That's what this is saying. And usually what's happening here is that our level curves get closer together in the direction of steepest, in the direction that's steepest. So that's kind of what it's doing. So imagine that this is actually like a 3-dimensional curve. Maybe this can be going downward or this can be going upward. going into the maximums or minimums. So this is going to be really useful, especially when we talk about maximums and minimums and trying to figure out where they are. Well, the gradient vector tells you where exactly the maximums and minimums are going to be just by following that particular path. So whenever I ask you for maximum rate of change, remember the direction in which you have the maximum rate of change will be wherever whatever the point is at the gradient vector, and the actual slope, the actual maximum rate of change, will be the magnitude of that particular vector. Okay, so that's it for these notes.